Hi everyone. I will talk about the results from the passive WiFi trials recently. Here's outline. First, I will explain the motivation of the Wi-Fi passive WiFi trials. And second, I will introduce the experiment description. And third, I will introduce the methods we use for different detection scenarios. For example, bulk detection, micro Doppler detection, and breathing detection. And also the relevant signal processing for these three domains detections. And finally, I will summary and give the future work. Here are the brief research questions for the trials. First is, in the indoor environment, we use the passive Wi-Fi radar. Can it detect single and multiple moving targets through wall? And the second is whether we can detect the micro Doppler signatures through wall. And the third is whether we can detect breathing, both through wall and through wall. For the experiment setup, for the surveillance and the reference antennas, we use the 2.4 GHz, 18 dBi antennas with the beam angle of 30 degrees. Here we only use one receiver surveillance antenna. And we use two USRPs as the reference and the surveillance receiver, synchronized by the MIMO cable. And we use the Edimax AP as the transmitter with the only antenna with 3 dBi gain. And we also use the Dell laptop, which is this one, for recording data and for the passive radar signal processing. Here is the scenario for the experiments, and here is the picture of the house. And this antenna is the reference antenna, which is very close to the wall, pointing to the position of the AP in the room here. And this is the surveillance, this is reference one, and this is surveillance antenna. The range, the distance between the surveillance antenna to the wall can be very, can be changed. And we have these experiments when the surveillance antenna is 1 meter or 2 meters and 4 meters away from the wall.
What kind of antenna is it?
Yagi antenna.
It's a Yagi, okay.
Yeah, here's the drawing of the room inside the house. So as we can see here, there's kind of a very long window. So it's not really a through wall detection if we put the surveillance antenna from this angle. So we put the surveillance antenna and reference antenna all just eliminating the window effect. So these are the walls. And the depth of the wall is like 33 centimeters. It's a brick wall. And here is our AP position.
Presumably it's a cavity wall with a gap in the middle.
Yeah, cavity wall. Here is the Wi-Fi AP, which is the transmitter, and it is 1.15 meters to the wall. Here is the wall. And the detection zone is like this square. So the area of the square is 1.2 meters by 4.4 meters. And we assume this square is our detection zone. And our target breathing here, and maybe for the bulk detection, the target is walking from this end to this end. And when we are doing the macro Doppler detection, our target is around this way. And or we can also do it like 1 meter or 2 meters distance to this wall. Yeah, here is our plans for the experiments. So first, we did the detection of the single target walking and the two targets walking. Second, we did the detection of the macro Doppler signatures. For example, swaying left and right, front and back for very macro movement. And third, we detection of the breathing, but these people need to stand near the wall and kind of still because it will influence the phase effect. Yeah, and all our detectors are based on through wall scenarios. Yeah, here's the basic ambiguity function. I guess you guys know it very well. So here is the ambiguity function, basic scenario. And here, this term do the cross correlation and then do the FFT, transfer into the frequency domain. But for the cross ambiguity function, we just change this one to the reference signal, and this one is the surveillance signal. Yeah, and for the cross ambiguity function parameters, For the sampling rate, we only use 2 megahertz because of the laptop processing load. It cannot do very accurate detection or the very complex post-processing method for the 20 megahertz, which is the bandwidth of the Wi-Fi signal. And for the detection of the range time is like 0.5 second, and the overlapping time is 0.05 second. And so in general, we split both the reference and the surveillance signals into 50 segmentations. And for each segmentation, we do cross-correlation, and we pick up a specific range, which is the target range. And we pick the 50 segmentation, which is the 50 points, and to do the FFT.
What does the waveform of the Wi-Fi look like?
Sorry, I didn't describe the signals.
Are you going to talk about it? Okay.
Yeah, but if I use the draw, so it's like, here's the time,
Mm-hmm.
and here is the magnitude. For example, here is 0.01 second, and for some time there are no signal, and then there will be a really big burst, and then come down. And then it will be a very short burst, just the synchronization of beacon signal. And then it takes some time, then another burst. It's like this. So the burst rate can be adjusted from the Wi-Fi AP or the protocols.
And what's the band, or what's the pulse
Bandwidth?
width? The pulse width of those pulses?
Here.
Yeah.
Yeah, it's like, this one can be changed on different protocols.
Oh, okay.
If a high rate, it would be 0.001 second.
Okay.
Really complete waveforms. Yeah, but it can change.
Okay.
Yeah. Yeah, so for the bulk detection is aimed to detect the constant Doppler when the targets are moving, not the macro Doppler, which is the arms waving or the breathing, the chest moving. So here are some limitations. Because the low range resolution of the Wi-Fi signal is only 25 mega, and the irregular Wi-Fi burst waveforms, for example, here the waveforms is not continuous, for example, and the ups down, or the edit. So it makes the frequency spectrum kind of messy. So 3 preliminary methods have been introduced. These methods are used for both the single target detection and the multi-target detection. First, it is the well-known clean algorithm plus the self-origin processing. Second, we introduced the standard deviation method. And third, we introduced the blind cell separation method from the audio signal processing. Here is the clean and the self-origin algorithm. So for the clean algorithm, we do 2 cross-ambiguity functions. For the first cross-ambiguity function, we do the reference signal and surveillance signal. And for the second one, we use the reference and the reference. And then we get 2 surface. So we subtract the surface from the surveillance and the reference from the reference and the reference. So this will give us a cleaner frequency spectrum. And the self-averaging method is aimed to make the smaller pixel value smaller and the large pixel value larger, just by using the square function and the summing up of the pixel values in the neighborhood of each pixel. So just like this. For example, if I'm focused on the ij pixel, and first I square the neighborhood, for example, I minus 1, I plus 1, j minus 1, j plus 1, and add them together as the self-averaging result for that pixel. So it will enhance the result for our target detection.
Does it get rid of some of your multipath? Is that what you?
Actually, so the clean algorithm would do the multipath elimination. I think the self-averaging is mostly important for the burst, the irregular burst waveform. It will give us extra ambiguities, not only in the 0 Doppler, but also on another some Dopplers. Actually, the clean and self-averaging works for the single target scenario, but not that valid for the 2 target scenario. For example, we cannot do one enhancement, just enhancing all the targets, all the Dopplers. So just for the second target, it also seems that echoes from the second target is lower than the noisy frequency component caused by the Wi-Fi waveform. So we use kind of like adaptive cell averaging and clean. So for example, first I got a surface I, and then I average the surface I, and I submit this one from the I to make the I plus one surface. And then I do this again, and again. So for the first iteration, the first target will come up, and then the first target will be eliminated, and then pick up the second one. So here comes the result. So here it is the cell Doppler history, and here it is the time, and the y-axis is the Doppler. So at first nobody is there, so because and then there's no Doppler detection, and here then comes one target moving from one end to the other end. So the velocity just changes from 0 to negative maximum and to 0 and positive maximum and 0. And this picture shows the one target and two target scenario and the differences between them. First, there's no Doppler detection. Second, then it becomes one target. And then comes two targets. For example, you can see here, two different velocities can be detected by the adaptive cell averaging algorithm. Yeah. So next, the standard deviation method has been introduced. For example, if you want to identify two targets, and when the targets are at different velocities, so what can we do here? So basically, for example, we are assuming that we have a vector, and the vector mean of the vector cannot be changed if there are two targets there, if the spectrum is kind of messy, but the standard deviation is changed. So it's very easy, so we just process standard deviation from both the positive and the negative Doppler band, so that whether it can give us two detections simultaneously. Here's the result. So here we can see one pulse here. This is the positive standard history, and here's the time. Here's the standard deviation amplitude. So when here's pulse here, it means one target is moving towards the antenna. And you can see here, when it is high, here, there's no response basically from the negative band. And then another one comes up. Yeah. We assumed to use this method to distinguish two targets detection. And from this part, the left one, these are the one scenario, for example, positive, negative, positive, negative, positive, negative. And then when two targets are coming, we can see here, one target basically at the same time. Here, the standard deviation comes up high at the same time when two targets are moving at different velocities. Because at one instant, a person cannot have both positive and negative velocities. Yeah, the third, we use the blind cell separation method. So we can think about this problem. So we regard two Doppler echoes from two targets as two separate sources. And our problem is then, if we only have one target to receive one mixed signal from two separate Doppler signals, can we distinguish the two separate Dopplers? Not from the frequency domain, but from the time domain. Yeah, so here, we choose the basic equation from the blind cell separation, where X is the mixed Doppler signal. After the cross correlation, for example, if we have the size of the X is 1 multiplied by n, which means for a period we have n samples, and we have only one receiver. And also the A is the mixing matrix and the estimation, which is the 1 minus n. For example, we have n independent sources. And the separated signals are S, which is under the estimation as well, which is the n multiplied by n, which is n samples and n targets, so n sources. And we can write this equation. And the problem is, the task is we need to estimate A and S simultaneously according to X. So it's like an optimization problem, convex optimization problem. So what we want to estimate is A and S, and we want to use this as the criteria for the convex optimization. For example, A is a mixing matrix, S is a separate signal. We want to make this reconstruction to X as minimum as possible, because this S, there are two vectors. These two vectors need to be mixed to X exactly. So the cost function, this term should be small. And the second term, because S is the separated signal, it is in time domain. And if we do here D is the IFT matrix and alpha is the frequency components with the D matrix. So we also want to make the alpha as sparse as enough, because when, for example, if we have two targets, the alpha is not that sparse than if we have only one target. So the problem is like this one. We need to solve this equation. Solve both alpha and A. Simultaneously updating mixing matrix A and the signal S. So what's the physical meaning of this method? I'm not sure. I guess it is like the beamforming weights of two antennas. For example, we have two antennas. We can cross correlation to get two mixed Dopplers, and we give them the weights to eliminate one Doppler, but and contain another Doppler signal. Yeah. So here comes the result. This is the experimental result. So we have two targets moving at different velocities, and the velocities are in the opposite direction. For example, here we have one positive velocity here and one negative velocity here. We want to separate them. Here it is the DSI. Yeah, and this plot shows the phase of the mixed Doppler signal. For example, the phase is like this, and here is the magnitude. Well, from the phase, we can hardly see anything from here. But in the frequency domain, we can see, okay, there's a little pulse here, and here is a little pulse here. Yeah, so after we do the blind sound separation, so here comes the separated signal 1, which means there's one target. The echoes from one target. We can see here the phase from basically pi to minus pi, and then pi to minus pi. So it seems that the frequency is 4 Hz, which means we have a negative 0.5 meter per second here. You can see from here there are some little pulse, but it is not as big as this one. And this is our target 1. And for our target 2, we can see here the phase changes in a different direction from minus pi to pi, minus pi to pi. And it is also kind of like 2 cycles, which means 4 Hz. And we can have here is 0.5 meters positive velocities here. So we separate one mixed signal into 2 separate signals, and these 2 separate signals have different frequency components. Yeah, so just to make the result more, seems it's like right. So here it is the iteration 0. We have a DSI component, a kind of messy positive velocity Doppler and a negative Doppler. And the phase is basically rubbish. And okay, after one iteration, we can get 2 separate signals. Here it is also the phase indication. Yeah, it's kind of messy, but this one looks a little bit nicer than this one. So we pick up this, and we can see here, some phase information has been extracted, which makes this positive one, because it is from the negative minus pi to pi. And after another iteration, okay, this one becomes very clear. Now for this one, it is a target here. Yeah, so the final equation we have here. We only have one target here. But this one, we have both this target and this target. So it's very easy. Where this plot is high, which ignore this, we have this one. So here comes the two separated signals. The separation, yeah. So here comes the results of the macro Doppler detection. The target is standing at 1.5 meter in front of the antenna. And first, we didn't do anything, and then we just swing front and back for several times here. And then we stop, and then we swing left and right. So here comes the result. This velocity is like lower than this one because the direction to the bistatic angle is kind of like to 90 degree. Yeah, and the results of the breathing detection. For the breathing detection, because when we're doing the normal breathing, the chest movement is only like 1 centimeter to 2 centimeters, and if we want to have a very strong power Doppler indication, we need a much higher, much longer integration time. But in the real time, we cannot do this. So we just didn't do the FFT anymore. We just do the cross correlation, and we'll pick up one point and plot the phase information of this time domain cross correlation result. Yeah, here comes the result. So the target is like near the wall, standing still, and the distance between target and the wall is only like 50 centimeters. And it's breathing, normal breathing. And here, the y-axis is the phase amplitude, and the x-axis is the time domain. So we can see here, when the chest is inhaling, it ups, and then exhaling down. Ups, down, ups, down, ups, down, ups, down. So for quite a few cycles. So we can see that it is possible that we can also detect the breathing in a through-wall scenario. But the limitation is the target needs to be stand very stable.
What are the units of the horizontal axis?
Horizontal axis, it is the time domain plots.
Yeah, what are the units?
Units, okay. So for 1 point, it's like 0.05. Yeah, so 0.05. It's like 80 seconds from this end. So so it's basically it's normal breathing. It's not very fast, and then not the, yeah, this is the scenario for the breathing test I have introduced before, I think. Yeah, so here comes the summary. So in this trial, we can prove that we can detect a single moving target detection through wall. And we can also sort of detect the multiple targets and using only one receiver. It seems difficult, but it seems there is a kind of performance to improve. Third, we have already done the macro Doppler signature detection through wall is also feasible. As before, so we do the breathing detection. For the future work, because for the blind spot separation in our scenario is like the undetermined, which means the receiver is smaller, the number of receiver is smaller than the number of sources, which is very practical because if we only have 2 antennas, we cannot detect only 2 targets. Yeah, so maybe next future work would be I will use the 2 antennas to detect the multiple targets, not only one receiver. And we are also not limited on the FT basis because we want the supports under a kind of basis to be as sparse as enough. If the sparser, then the target becomes very obvious. The second is maybe we can introduce some sequential detection results to provide more reliable results. For example, in a very short time, the velocity of the targets can be the same, and the supports and the bases can be the same. So we can use the multiple measurement to give a more reliable result. And the fourth, for the breathing detection, several filters should be used to eliminate the spike phases point because of the gap between the Wi-Fi burst. It's because this Wi-Fi burst is irregular, and then it makes some phases not valid at the same time. It makes some a little big spike for some time. Yeah. So thank you. And any questions?
Have you looked at applying kind of a SVD analysis on the signal?
SVD?
Yeah.
Yeah.
Because that seemed like as you were extracting the positive and negative components in a previous method, that may be something
Yes.
possible using SVD as well.
SVD.
Single value
Yeah,
decomposition.
yeah. So yeah, it's a very good option, I think.
It might not be very good real time because it's probably computationally
Yeah.
heavy. But
Yeah, yeah.
later offline processing it might be quite good.
Yeah, the SVD one, yeah. So it's like the low rank decomposition, or?
Yeah, I think it's similar to that kind of processing, yeah. In
So-
MATLAB it's very simple to implement.
Yeah, so we do SVD and we get a diagonal matrix. And we pick up the
Yeah.
value from the diagonal pixels,
Yeah.
diagonal values.
Yeah, you can do that.
Okay, I will try that, thank you.
Yeah, no worries. I'll show you some code that I did.
Yeah,
if you want.
sure. Okay.
Nice.
Single value decomposition.
Right. Thank you very much.
Thank you.